of white blood cell differential scattergram. So this will be given by Mr. Wong Ming, a microbiologist in pathology department of Hospital Sultanah Nora Ismail, Batu, Pahat, Johor. Okay, so Mr. Wong holds the positions of Science Officer Grade C12 with a degree of Science is Microbiology from University Malaya. So more interesting is this our young squire also has Master of Business Administrations from UMS and Masters of Environment Science from UNIMAS. Okay, so which has he attended while working in Hospital Labuan and Hospital Bintulu. So he is recently working on an ongoing project for Salmonella serotyping, antibiotics resistance. And then nevertheless, his current interests are into AI and machine learning in clinical laboratory and based on probability in laboratory quality control, measurement sensitivity, and automation using Python. Okay, so it is a great for the visionary scientist to join us today with his talk. So, well, ladies and gentlemen, so without further ado, let's welcome Mr. Wong Ming. For you, Mr. Wong.
Okay, thank you, Jane. Thank you for the introduction. Good morning, everyone. I think I'll start straight away with my presentation. Let me share my slide. Okay, can you all see my slide? Can everyone see my slide? Okay, let me start first with the topic of my presentation today. Deep convolutional neural networks, CNN, with few shot learning, FSL, for malaria detection using full blood count differential scattergram images. This is actually the slide that I used when I joined the Johor Research Day competition last year. And I'm happy to inform everyone here that my team and I, we got first prize for this research. My team are comprised of there are 3 of us in the team. I'm the principal investigator, and together with Dr. Azlina, she is also from Hospital Sultanah Nora Ismail, Batu, Pahat. Another one of my team member is Raja Saidatu Nadia, and she is a biochemist from Hospital Sungai Siput. So before I start this presentation, let me give a few simple introduction into what is AI, artificial intelligence, and machine learning. These are actually very big concept, very big concept that is very famous now. And convolutional neural network, CNN here, they are actually one of the method that we can use as part of the machine learning research methodology. Few shot learning is also another method actually. and it is a very new method actually. FSL has only been introduced, I think, in 2018, if I'm not mistaken. Okay, malaria detection at the moment, it is, I think most of us here we know what is malaria detection. I'll go into a slide. I'll explain a bit more into later on in my slide, as well as full word count, FBC, differential. This will be also explained in my presentation later. Cool. What has been done in the literature? We can see that there has been a lot of research done on FBC. They use FBC scattergram also to detect malaria. But however, in this research, most of them they use human expert, meaning that a human expert is used to interpret the FBC result to detect whether the sample is malaria positive or not. Okay, so this is this part here. And on another side of the CNN has also been used quite extensively in medical images, mostly in medical images. Okay, at the moment, a lot of the research they concentrate on microscopy as well as radio imaging. Okay, in radio imaging, they use CNN to detect tumor detection, or to enhance X-ray or other images, so that it is easier for the human to interpret the images. In microscopy, in malaria microscopy, on the other hand, CNN has been used to classify whether the species of the parasite, to identify the species of the parasite. It is like we capture an image of the parasite under microscope, then we send it to the AI. The AI will try to identify the species of the malaria species. So in this, in my research, however, this is how I presented. This is how I propose what we'll do in this research. But again, we'll use the existing connection between FBC and malaria. However, I'm using CNN to interpret the image of the FBC images to detect malaria. So I'm not using the human expert anymore. Okay, we don't need a human expert to read the FBC images anymore. Right, the FBC scattergram images. Okay, we'll use the AI CNN to read the FBC, to interpret the FBC scattergram. And instead of using medical images, now I'm using the machine generated the FBC scattergram images, the images generated directly from the analyzer. So these images will be interpreted by the CNN, and if a malaria is present, it will be detected as positive. However, in this research, we introduce a new innovation. Okay, a new innovation into machine learning. This innovation is called FSL, few shot learning. To the best of my knowledge, this is the first research that uses FSL in medical AI. So So these are the two most important innovation actually that we use. These are the two new approaches that we use in this project. First, we use the CNN, and then we use the FSL. Why do we use FSL? I'll explain it a bit more later. So the problem segment in this research is malaria laboratory. Malaria laboratory diagnosis depends on microscopic blood smear examination. I think most of the microbiologists here, they will know that this diagnosis, this methodology is very time consuming and you require expert interpretation. Someone has to be really skilled at looking at the blood smear microscopy to interpret and identify malaria infection. On the other hand, some of the lab they use RTK, rapid test kits, to test for malaria. These lab are usually they have very low workload on malaria. That's why they are not skilled in microscopy, and that's why they can afford to use. They have to use rapid test kits instead RTK. However, we know that RTKs they have limited coverage. There are 4 malaria species commonly detected by RTKs. However, the 5th species, Plasmodium knowlesi, which is endemic here in Southeast Asia, not all the RTK can detect this species. So it has limited coverage. RTK has limited coverage. So the objective of this research is to apply deep CNN with FSL to diagnose malaria using FBC scattergram. Basically, this is a proof of concept research. Okay, in this research, we try to see whether the application of deep CNN, application of AI, can be used to diagnose malaria. So the first question that we want to answer is, can we do it? And if we can do it, how to do it? What method can be used? What method should we use? And finally, why should we use this new method? Why should we use AI to diagnose malaria? Okay. This research is quantitative in nature and retrospective. Quantitative in a sense that images, once we subject images to machine learning, they are actually looking at the value of each of the pixel in the image. So each of the pixel has value. So this is why this type of research is considered quantitative. Retrospective and cross-sectional because the data that we use is from previous years, 2023, from January until June, and so it is only a cross-sectional snapshot of the whole year in our lab. It is also multi-center because it's a joint effort from Batu Pahat and Sungai Siput. Then next, for every positive FBC, positive FBC here means the FBCs comes from the sample of the for the FBC analysis contain malaria, is infected by malaria. So I'll call them FBC, positive FBC. So in the same sense, negative FBC means that the FBC samples does not is not infected by malaria. So negative controls were used also in this in this analysis. And negative control are collected 30 minutes before and after a positive case. So we try to minimize any variation caused by the machine, the analyzer, or the operator from that lab. Modeling of the AI model is built using a supervised machine learning algorithm. Why we call this method as supervised? Because we tell the machine during the development phase, we tell the machine learning algorithm that this image is a positive image or a negative image. So we tell them the answer. So the next step is on data splitting. Even in traditional statistical modeling, we still need to validate our model. So in machine learning, we have an additional step. We call them training, testing, and validation. In training, this is where I mentioned in supervised machine learning. In training, we train the machine, we train the AI model with labeled images. So this we tell them this image is for positive and the other image is for negative. So they will know that this which image are positive and which image are negative. Then for every cycle of training, the model will be tested. So if the accuracy is low, it will be retrained. So the process goes back and forth, training and testing until it achieves the accuracy level that we set. And finally, the validation part. In this project, the training and testing data comes from Batu Pahat. However, the validation data comes from hospital Sungai Siput. So I wanted to test whether the model can, whether we can generalize the use of that model. We can transfer the model to a different setting, to a different location, or to a different hospital. So during the whole process here, the training, testing, and validation, we have used a few evaluation metrics. The major one is the binary cross entropy. Binary cross entropy is an evaluation metric commonly used in machine learning. However, it's actually quite similar to accuracy. Okay, I think most of us will know what is accuracy, right? So, however, binary cross entropy, as the name suggests, is an entropy. So it's an entropy. So it is detecting loss. It's detecting error. Okay. Yeah. So instead of accuracy, it is detecting error. So we are trying to reduce the error in the model instead of increasing the accuracy of the model. Of course, these two are related. The evaluation metrics are related to each other. So this is the methodology that we use. I simplify the whole thing. I try to explain in detail each part of this research methodology here. So firstly, data collection. So we collect the data that we use is this FBC scattergram. Okay, I use only 14 positive FBC and 28 negative FBC. So what are scattergram? I think for those of you who have been who works in hematology lab, they are quite familiar with what is scattergram. But here I try to show you what are scattergram. I think most of us were familiar with FBC analysis, and the machine will produce a graph. We call them scattergram here. It is something like this. Okay. Okay. But actually, the machine that I use is 6Mac SN1000. So 6Mac SN1000, they produce actually a few scattergram. Okay. What are scattergram? The data for scattergram comes from this. This is the flow cytometry. So in flow cytometry, the light source will come or shine on the cell. It will be scattered, and this is what we call forward scattered. Then there are also side scattered, and the light source, we can also change the light source to a fluorescent one. So that's how we get this kind of graph. This is FSC, forward scatter. This is SFL. This is the fluorescent light, and this is the SFL. Again, this is SFL, the fluorescent, and then SSC, the side scatter. Actually, if we plot the whole thing on the same graph, this is how it looks like. This is SSC, FSC, and this is SFL. Okay, this is the whole thing. This is how flow cytometry. Okay. So normally, this image is in this is one graph by itself. But in this research, I combine all the three graphs into one, and I change the background to black color. This is just so that it's easier to for the machine to interpret. I change the background to black color. So this is just the first part, the pre-processing. So after pre-processing, the image is sent to the model, and we start building the model. Then the training and testing part goes back and forth. This part is repeated multiple times. Here we only use data from HSA9, okay, Hospital Batu Pahat. Then after the model has been built, we use the data from Hospital Sungai Siput for the validation. So again, I want to elaborate a little bit more on the model that we use. Okay, so this is a diagrammatic presentation of how my models look like. So the first part here, this is how the size of the image, the pixel size. So it is 843. The height is 843 pixel times the width is 281 pixel times 3 layer. There are 3 layer, different color, RGB, red, green, and blue. RGB layer. There are 3 layer. So after the first convolutional layer, this is the layer. After the first convolutional layer, the image, the data has been transformed into this different how to call that, in a different format. Okay, so 841 pixel times 279 pixel times 64 layer. So again, in the next pooling layer, the next layer is a pooling layer. Pooling layer is basically the averaging layer. It average out all this data into a new form of data. So after averaging, the data becomes 420 times 139 times 64. So this is a new shape of the data now. So this is the second layer, second convolutional layer. This is the second convolutional layer, and after the second convolutional layer, we get this shape of data, and finally, again the pooling layer, and we get another form of another shape of data here. And finally, we flat this image, this data, we flatten it, and it becomes like a linear data. So this is the neural network part. This is the convolutional layer, and this is the neural network. So there are many neural network here. Each node represent one node of neural. So this node, they are all connected. That's why we call them neural network. So there are 256 nodes inside here. So this is the first neural network, neural layer. Then this is the second neural layer, 64 nodes. And finally, this is the output layer. Okay. So from this image, it goes through the whole process here, and you arrive at this output. The output will be in either 0 or 1. So 0 meaning negative and 1 meaning positive. Okay. So whether it will tell us whether this image here is positive for malaria or negative for malaria. For those who are familiar with regression analysis, each part, each node here, they are actually one, the whole one equation. So there are 256 equations here, this layer, and then we have 64 equations in this layer, and all the output of this 64 equation will return a single output. Okay, so this is the neural network. Okay, for most of the time, for the conventional neural network AI model, they require a lot of data, a lot, even in the sense of traditional statistical modeling. They require like hundreds, like 100 or 200 data. However, in machine learning, will require much more. We might need 10,000 or even up to 100,000 or millions of data, and this is quite impossible in medical research. Actually, this is one of the biggest problem faced by medical AI research. So, however, by introducing the FSL method, I managed to cut down the data size requirement to only this 42 the 42 number of data that we need. So this is a very new approach that I introduced from this project. So let's look now at the result. And remember just now I said with the evaluation metric is loss. Is the binary entropy, binary cross entropy. It's actually detecting loss. Loss meaning error error, the degree of error in the model. So let's look at the training loss here, the red color one. So we can see that epoch meaning cycle. So the first training cycle, second training, third training cycle. So these are training cycle. So first, second, third. So we can see that the loss is reducing. But after cycle 16, it seems like the loss is going up. Okay, I stop here, but actually, if I proceed, probably the loss will go up. So the accuracy is reduced after this. Now, after that, at each cycle, the model is being built. Once the model is built, we test it on the data again. So this is the testing loss for the model. Okay, so the testing model, the testing loss is also reducing. We can see here it's also reducing, but it seems like it plateau out here. So, and this at this level, this is roughly what we call about 95% accuracy. and this is about 99% accuracy. So it seems like the model accuracy is roughly between 95 to 99% during the training phase. Okay, so after that, we use the model and the data from Hospital Sungai Siput, and we tested it. So do remember that the model has never seen, the AI model has never seen the data from Hospital Sungai Siput. So far, it has only been trained and tested on Hospital Batu Pahat's data. So the data from Hospital Sungai Siput is completely new to the machine. So it has never seen the data before. And we tested a total of 34 images from Hospital Sungai Siput. And we can see that it has 100% sensitivity. Sensitivity is 10 divided by 10. We have 100% sensitivity. Specificity is 87.5%. 21 divided by 24 here. And so we have false negative, 0 false negative. And the false positive rate is 12.5%. Overall accuracy is 91.2%. Overall accuracy. So this is on completely unseen data that the model has never seen before. It is a very good, in my opinion, it is a very good achievement. It has it has done surprising well. And again, the 34 FBC analysis, the duration it took to analyze 34 FBC is less than 10 minutes. The model is actually very fast. 34 FBC in 10 minutes. Minus, if we look at under normal circumstances in my lab, if we examine 20 malaria slide, malaria microscopy, the PFMP smear, if we examine 20 slide, it would probably take more than 8 hours for one staff. If there's only one staff looking at the slide, I will take more than 8 hours. So imagine the time saved here, 34 FBC. 34 FBC meaning like 34 BFMP. It will take less than 10 minutes. So I analyze this further on. So let's assume that we have 111 specimen with 10% prevalence, meaning that 10% of these specimens are positive. Okay, so assuming we are doing it manually here, 111 slide, it will take 46 staff hour, and it will cost us 828 ringgit. Okay, so if we choose to use RTK instead, we screen all the 111 tests using RTK. So we'll use 111 kits. It will still take about 4 staff hours to finish testing the specimen. Without confirmation, without microscopy confirmation, this is only using RTK. So even by using RTK, 111 specimen will take you 4 staff hours, and in total it will cost you 1,000 plus 1,182 ringgit. On the other hand, if we use the AI model, so with 10% prevalence, and the level of accuracy in my model will probably detect 24 positive and 87 negative. This 87 is true negative, because we have 0 false negative. So all 87 here is positive. And the 24 here, there are false positive inside for 24 here. So we still need to confirm all the 24 sample here. So this 24 sample will be confirmed using microscopy method, and it will take us 10 staff hour to finish the 24 here. So, but then it will only cost 180 ringgit if we choose to use the AI model. So a lot of saving here is like up to 4.6 to 6.5 times the saving compared to manual and RTK. So finally, we move on to the discussion part. We have successfully proved that this diagnosis of malaria using AI is applicable, can be used in our lab. It is very high. It has very high accuracy, and by using FSL, we have overcome the data limitation that is faced by a lot of medical AI research. All the methodology used to develop the model, the AI model, everything, they are all open source, meaning it is free. They are free to use. I don't use any pirated application here. All the applications that I use are open source and they are free to use. So there's no cost here. There's no cost to build this model. It can be used in a real world application. We have tested it in two different hospitals, and in future maybe we'll try to brought in more hospital. Then we can try to see if it can be used in other hospital as well. Okay, it's very cost effective as I show you just now, and highly efficient. It's very fast. So the conclusion finally, the future of AI-powered malaria diagnosis. We have revolutionized how malaria screening can be done. We can, from now on, if we use AI model, we can do mass screening of malaria. Previously, we do malaria screening one by one, okay, one slide after another by microscopy, or even using RTK one by one. But then using AI-powered AI model, we can do mass screening. I can see that it can be applied in, let's say, last time when I was in Sarawak, confusion microbiology lab, they will try to screen for malaria in all the blood donation. It is quite difficult to do. Let's say today you have 100 donation and you want to screen everything using microscopy. It's quite difficult to do. It's almost impossible. However, using AI, it will take you like 1 or 2 hours to finish all the screening. Okay. Of course, if there are anyone is interested, I'm open for further collaboration as well. And more research and R&D, research and development is needed. Is still needed to see if we can explore into different field in the laboratory using AI. Okay, not just microscopy, not just malaria. We can explore into a lot of field in the lab using AI model. With that, this is my last slide, and I thank you all for your attention. Thank you. Testing.
Hello?
Jane,
Okay.
just now cannot hear your voice.
Oh, is it? Okay.
Yeah.
So we have a few questions here from the attendees. Okay. So says that it is a very interesting research. Congratulations, and to adapt for diagnostics. So, what more to be done, and what is the minimal setup to perform this and adapt as a part of the method in hospital level in terms of hardware and operational system software or etc. Get the question?
Jen, I think the question is they are asking about how to adapt this
Mm.
this model into the lab, right? So
Yeah, how we can use it, or how we can take this model to perform tests in hospitals.
this is actually what we call the deployment stage, the deployment of the AI model. Um, it's actually at the moment I haven't been into the deployment stage. But the deployment should be quite easy actually. Technically quite easy. But administratively it's a bit challenging actually. Because how to say, most laboratory, I believe, most laboratory they don't have what we call high-end computer, high spec computer. Okay,
Yeah, we don't have that.
without high spec computer, it's actually difficult to develop the model. But then to use the model is actually quite okay. To use the model is actually quite okay to use normal PC. Once you develop the model, then you use it. However, the easiest way is still to use what we call cloud computing. We do it online. Okay, but that is where the challenge comes in. Will be facing issue of confidentiality. We face issue of sensitivity of the data once we upload the image online. We can exclude all the personal information from the images actually. That would be an additional step. It is not very difficult, but still some of our director, like I would say some of our pengarah, they are still very concerned with confidentiality. Actually, so that is the challenge here. If you want, actually, it's actually quite easy. Technically, it's actually quite easy to deploy. Is the challenge is in administration.
So it means that this software is an open system, so everybody can look into that, into the data, right?
The software that I use to develop is open source. But the model the model is with me lah. So if you want to use it, you have to ask for the model from me lah.
Oh.
The model is
So
not open.
So the next question is, how do you plan to continue or build or improve on this study, and how can other hospitals participate in these studies also? So there's somebody is interested in joining you to do the study also.
There are many ways you can proceed. There are many ways you can how do I say to continue this project because at the moment the model is specific to Sysmex XN 1000. So if your lab is using Sysmex XN 1000, you can directly use my model. But if your lab, let's say you are using a different analyzer, a different FBC analyzer, you will need to build the model again. The model, the process is simple, but then you need high spec computer to develop the model. Again, you can do it online. I did it online. just to share with everyone here, actually, I try to do it locally in my laptop. It's a gaming laptop, considered high-end laptop. It still took me like 2 days to build the model. Meaning I left my PC running 48 hours non-stop, and still not every time the model came out successful. So it's difficult to build the model, but actually quite easy to use it. To use it quite easy, just like I said just now, 34 FBC, we can finish the analysis in 10 minutes. To use it is quite easy. To develop is quite difficult. So how you can the future lah, the future of this is maybe you can build a different model for a different analyzer, or a general model for every analyzer. I don't know. Maybe it can be done. Other than that, we can also go into different field, as I said just now. Instead of malaria, maybe we can go into different disease. Maybe in or a totally different field actually, like hematology or biochemistry. Okay.
Okay. So I think that should answer the question just now. So the third question is, I think there's a lot of people interested in this. The question is, this person is from MKK. May I ask, to what extent is the AI able to perform diagnosis and specification or human or zoonotic species or parasite density stages?
Okay. This is a very interesting question now. It is something actually that I found out also during the model development. The data from Batu Pahat that I use to develop the model, there are actually only two species inside there. Plasmodium falciparum (PF) and Plasmodium vivax (PV). The only PF and PV. I only use PF and PV to build the model. However, the data from Hospital Sungai Siput, they are knowledge, Plasmodium knowledge, PK infection inside it, and it is still detected. It is still detected. So it's very interesting in the sense that it is not trained on knowledge, but it can still detect knowledge. However, I'm not very sure if the model can differentiate the species or not. I'm not sure. I haven't gone into that. That one I'm not so sure. Counting part, I'm also not so sure. But parasite density, there are other researchers. I have seen other papers doing parasite density using AI model, and I think it can be done to detect parasite density. Stages also. If you have pictures, if you can take images, microscopic images of the malaria stages, malaria parasite stages, definitely it can differentiate. Definitely it can differentiate the stages. Again, just now, regarding the speciation, the species differentiation, if you present it with present the model, if you present to the AI, let's say this image is PF, A is PF, B is PV, C is PK, something like that. Definitely the model can be trained to differentiate species. But in my research, I use FBC. I don't use microscopy images. So I'm not sure whether we can differentiate species from FBC scattergram. Okay. I think I hope people are clear with my explanation. Jen, I cannot hear you. Yes, can hear now.
Okay, so I have problems with my mic. I'm sorry. So I hope that's the answer. Mr. Wong answer all the questions, but there's one person who asking to open the mic to ask question. So
Okey, Assalamualaikum dan selamat pagi. Saya Zuhaimi.
Zuhaimi.
Mr. Zuhaimi.
Okay, first of all, thank you so much for your presentation. It's very interesting, even though I just have a way to listen it. And then congratulations to you, Wong, because I think it's from the feedback that we have seen, it's quite new lah, very interesting topic. Cuma there's a few things yang I want to clarify with you. Okay, this is still what do you call it, development stage or having using. Okay, that's the first question. Second, if already used, is there any hospital having used this? Batu Pahat pakai ke? Ataupun ada hospital lain? Okay. And then the third question is that similar like other analyzer? Because I didn't hear on the beginning of your talk. Okay. So I don't know what is the method is, the protocol and so on. So because what I know is there's one analyzer, hematology analyzer. Okay. They can also using a screening malaria, but the method is, I'm not mistaken, is spectrophotometer or something like that by the image. Okay, is that similar with you or different thing? Okay, for the three questions to you.
Okay, thank you, Zuhaimi. I try to answer the question one by one. The first question is actually on the stages of this project. Actually, at the moment, we have passed the development stages. We have also done field testing. Running the model in from using data from Hospital Sungai Siput. That is the field testing stage. Okay. But the deployment, no. This is also second question now. Deployment, no. I haven't deployed the model anywhere, not even in Batu Pahat. In Batu Pahat, we are facing the problem, the administrative problem, as I said earlier. Patient confidentiality, a very big issue here. So no, I haven't deployed anywhere. But Hospital Sungai Siput is trying. They are trying to deploy the model there lah. Hospital Sungai Siput will be the deployment will be done online. In Batu Pahat, actually, my pengara wanted it to be deployed offline, locally. So we are actually in the process to get a very good PC, a very good computer that can run the model because we don't want to run it online. So in Batu Pahat, no, I haven't deployed it yet. And finally, your last question on different analyzer. Yes, in my study, I use 6MEC XN 1000. There are many analyzer, and from what I remember, the analyzer by Abert, I forgot the brand, the version, the model. The analyzer by Abert, they claim they can detect. They claim they can detect malaria. Actually, the new model from Sysmex are also able to detect malaria. So I'm not sure whether they are using AI or they are using a fixed algorithm inside the analyzer. That one I'm not so sure. Right? But using AI is more, what do you call? It's easier to generalize. The pattern is not limited by the company. we can share. I think that's my answer lah.
Okay, any question, Cik Zaimi? Is that all? There's one person, Encik Muhammad Azra Azman, asked that can the model assist in the detection and categorizations of changes to RBC or WBC? Can the model assist?
Oh, I see. You're trying to like characterize RBC and WBC. This is from hematology point of view, is it? If it is from hematology point of view, definitely there are research, there are paper already done on this actually. Let's say they're looking for any abnormality, RBC abnormality. It can be done using AI model, but not my model lah. You have to build your own model for this.
Okay, there's someone asking also, Mr. Muslim, I think. It says that this AI is for detection of positive or negative only, or is it mean that it's just for qualitative or also quantitative?
In my research, this is I focus on positive, negative only. The value that came out actually from the model it's not exactly 0 and 1. It's actually the value is 0 until 1. So the higher the number, like let's say 0.98, this number is actually representing the probability of the sample being positive. So 0.98 means 98% that this 98% that this how do you call it? This sample is positive for malaria. That's actually how I program the model. Okay, you can do it actually in a different way. This is classification model. You can do it on quantification or species differentiation, as someone suggested just now. You can do it that way also. So if this, let's take example for species differentiation. At the moment we have 5 species. So the output will be like 1, 2, 3, 4, 5. There will be 5 output. And the model will tell you which species has the highest probability. Then we'll take that as the final result. That's how we use AI model. Okay.
So is there any suggestion for graphic cards that we should use in the PC, in our PC, if you want to build the model?
The graphic card, the GPU that I use in my laptop, if I'm not mistaken, is I forgot, it's the 5 series, I think, and that will take like two days, 48 hours to build. But then when I use online, the latest GPU, it takes about half an hour to build the model. This is an online GPU lah, online GPU. So I think if I have the latest GPU in locally, I can do it offline. Probably I can do it even faster than online, because online there's still the network, the connection limit, the connection limit there. So even online, it took me half an hour to build. But if I do it locally in my computer, in my laptop, 48 hours, still no guarantee.
Okay, it means that we have to have a high spec computers and with advanced graphic cards, right?
Yes.
To do the model, so it can run faster. So was it available now? It's just for our usage, daily usage, right? It's not suitable. So any more questions?
Jen, I just want to add.
Mm-hmm.
Actually, to use the high-end GPU, high-end graphic card online, it's actually quite cheap at the moment.
I see. So we can buy it online.
You don't buy, you rent the graphic card online. Renting.
Oh, I see.
So
Renting the card.
they'll rent to you, I think the rate is about 10 ringgit per hour. So this model will cost you like 5 ringgit only, like half an hour sudah habis kan. So 5 ringgit finish already. You don't have to buy the PC.
Yeah lah. Okay, any more questions? Front floor, please.
Hi, good afternoon, Mr. Wong. Yeah, we do.
Yes.
Okay. Actually, I just want to add on to what Mr. Zaimi just now was asking, like, because I previously had used the Abbott Celldyne Ruby. Actually, they claim can actually detect the malaria parasite lah in their through the FBC samples. That was a machine lah to add on for you. And actually, AI in detecting malaria is quite new, but I'm not sure. Are there any other research going on out there besides your topic? And another thing, just want to ask you, have you tried to publish it in any article journal?
Yes, we do. Actually, I'm in the process of publishing this paper. It has not been accepted yet lah, so I'm not sure when it will be published. And yes, about the analyzer, as you mentioned, Ruby, I remember the name now. Ruby, they say they can detect now. But I'm not sure what method they're using. I think they're using like a fixed algorithm inside the analyzer. I don't think they're using AI. Anyway, using AI to detect malaria, there are a lot of paper actually. There are a lot of paper online already. It's just that a lot of this paper, they concentrate on microscopy. They use microscopic images and AI. The AI will interpret the microscope images. In my project, the AI interpret FBC scattergram. So to the best of my knowledge, I think this is the first time people do this. Previously, they use human expert, as I present earlier. They use human expert to interpret FBC scattergram. And I like to add a bit more of information here. Most of these human expert, their sensitivity level is only up to 86%. Compared to my AI model at the moment, my AI model is 100% sensitive, so you don't miss out any infection. But human expert, they still miss out. The highest level of sensitivity is only 86. Most of them at around 50% only. So it's like a flick of coin, positive, negative. Okay.
Actually, Mr. Wong, this is a very good novel research, I would say. So hopefully you can get it published, and it's a groundbreaking if you can really get the model to run on the ground. So the hospitals going to really be helpful. But eventually we are going to lose the experts who are looking for the malaria parasites with the microscope lah. But it's not an issue, I suppose, in this coming technology.
Yes. I agree with you.
Okay. There's the last question from the floor. Okay. It says that will AI affected by degradation WBC? And since this system observe FBC, can we assume that phagocytosis, what phagocytosis, malaria parasite are also captured by this system?
Okay. Actually, in my project, I try to eliminate any how to say the positive data, the positive FBC. I took the positive FBC actually before and after treatment. Before and after treatment started. Okay. Before and after treatment started. So once the treatment has started, I think there will be degradation on the malaria parasite itself, and it is still detectable by my AI model. WBC degradation, I'm not so sure because FBC usually they'll run it immediately. So that one I'm not so sure. If for example the sample has been left there like more than 4 hours, then they run the FBC. I'm not sure whether it is still applicable or not. But usually under normal circumstances, we'll reject that kind of sample lah. So I'm not sure whether it will be affected or not. But treatment, yes, I have tried to check whether the treatment will affect the detection or not. It seems it is not affected. As long as they are still positive, the slide is positive, it will be detected. And then
Okay.
lastly, about phagocytized malaria parasite. I'm not so sure. I might need to look into this. I do not know. I'm not able to answer at the moment.
So there, Mr. Lee Kok Chin asking that how to download the model of AI because they also use Sysmac machine for FBC.
Mr. Lee, thank you for your interest. You cannot actually download my model. What you need is actually you need to set up my model at your place. The setting up is what we call the deployment stage. That one is not very difficult. If you're interested, we can discuss later on. But you don't simply download the model. You need to set up the model in your place.
Okay. For all the attendees, I hope that's answered all your questions. So any questions or any interest towards Mr. Wong's research, you can further contact him, okay, personally. So so I think the time is up. It's 12:11 already, so we will wrap this talk. And thank you, Mr. Wong, to join us today. And we are very honored and pleasure for your information. And I hope we can have another session with you again.
Okay.
Okay, that's all for now. So all the attendees, I hope you can fill up the forms that we put in the chat box. So you can please, and also your feedback form, and if you have any topics you want us to bring up or any speakers that you can suggest to us, so we'll be free to have your put your suggestion on the feedback forms. Okay, so for now, thank you and assalamu alaikum.